I know the audience are expert in these areas, and if I say something ridiculous, just stop me at any time. So here is a plasmasphere. So we're on the left panel, we're looking at the image set EUV image of a plasmasphere before and after the storm. So you can see that the size of the plasmasphere shrink significantly after the storm, and there's a drainage plume generated on the dusk side of the plasmasphere. If you put a high energy neutral atom image together with this EUV image, you will see the ring current forms a roughly complementary shape with the plasmasphere, and you can see some overlap at the dusk to noon sector in the plume region. So this complementary shape of the ring current and with the plasmasphere may indicate the ring current can be related to the erosion of the plasmasphere. Next, it is the SED or TEC plume. So during a storm event, we often see that the ionospheric total electron content increase as a storm positive effect. And in the noon to dusk sector, enhanced density plume structure extend from the mid-latitude region toward the polar cap, and this is so-called the SED or TEC plume. And if you map the this TEC map into the equatorial plane following some magnetic field line field profile, so you will see that this just the contour of it looks just like the shape of the plasmasphere. So this kind of connection between the plasmaspheric plume and the SED plume were first reported by Foster et al. In that famous 2002 paper, and where he first plotted the equatorial plane view of this is ionospheric view of the TEC, and he mapped the TEC contour at 50 TECU to the equatorial plane, and he plotted this plasma pulse location using the EUV image. So it can be shown that the two plumes overlap each other. So this phenomenon was simulated by the SEMI-3 RCM model, and they successfully reproduced this plume overlap. So like this overlap or joint evolution of this two plume indicates magnetosphere ionosphere coupling between the two. So for other observations in Foster 2006 paper, they mapped the they plotted the EUV of image of the plasmasphere as well as the TEC equatorial mapping, and they also put the DMSP measurement of the ion drift velocity. So they find that at the west edge of the plasmasphere as well as the TEC they find this velocity peak identified as subaurora polarization stream. So this indicates SAPs may related to this plume development. To systematically investigate the development of the geospace plume, we employ the newly developed MIT-coupled model, multi-scale atmosphere geospace environment. So basically, you can see there are four major components of it. First is a global MHD coupled with a ring current model, rise convection model. So in each coupling cycle, it will will pass plasma moments to the RCM boundary from the MHD side, and also the electric field is calculated by remix to using the field line currents passing from the MHD. And this potential will drive both the ring current model as well as the upper atmosphere circulation model, TIGCM. So meanwhile, TIGCM will take electron precipitation information. So it will track the it will self-consistently track the electron and ion density, neutral winds, and feedback conductance to the ionospheric potential solver. So there are some major components in the model that has been added to for the purpose of this study. First, we put a dynamic plasmosphere as a zero energy channel inside the RCM. So basically, what drives the plasmosphere channel is E cross speed drift plus the plus the rotation. And this plasmosphere model is also initialized by the Gallagher model. So you can input different KP index of that event for the initialization. Then it will feedback its cold density combined with other plasma density back to the MHD model. For the precipitation, now we have two kinds of electron precipitation. One is a monoenergetic precipitation from the MHD. Basically, the electron is accelerated by the field line potential drop at the region where the thermal electron cannot carry enough current for it. So for the diffuse precipitation, it is informed by the rest convection model. Basically, it's included with wave particle interaction causing the thermal electron to scatter into the loss cone. So lastly, it's a TIGCM model, which is the most important component because it tracks the TEC content, and it feedback the conductance consistently in the model. So for the science question we're going to answer is what causes the joint evolution of the plumes? Second, who plays a major role in shaping the plasmosphere and the geospace plume? And thirdly, what is the relation between the ring current buildup and the geospace plume development? The event we choose is March 31st, 2001 superstorm, where the image satellite and the DMSP are both in operation, so we can get a better data or a view of the plasmosphere geometry. So this is a CME-driven superstorm with DST dropped to minus 400 nanotesla, and it has two periods of negative VZ, but in this study we will just focus on the first period in the shaded area. Here is the simulation results. The top left panel is a ring current pressure profile, and on the right is TEC mapping to the equatorial plane using the magnetic field model magnetic field information generated by MAGE. And also the thick black contour is the plasma pulse location. Also for this equatorial plane potential, you're seeing it's a combination of the corrotation plus the ionospheric potential mapping. Here on the bottom, it is field line current as well as the ionospheric potential contour. On the right is TEC tracked by TiGCM and the potential generated by TiGCM itself. So here I categorize the each variable at different stage of the storm. So at pre-storm, you can see everything is the potential is dominated by the co-rotation. So that's why you see this circular shape of the potential contour. Here there's nothing much in the ionosphere, in the field line current, and here TEC, you can see some enhancement in the a higher TEC at the noon to dusk sector. And this is their equatorial mapping. You can see the plasmosphere in pre-storm, it's still in a circular shape. At the initial phase, there are already some solar wind driving, and you can see the double cell convection pattern has started to establish, and you can see due to the driving, the plasmosphere has a tendency to extend toward the day side, and there's a plasmospheric finger generated. For the early main phase, you can see there are some pressure, ring current pressure start to establish, and the double cell pattern has been further enhanced, and the peak of the TEC has moved toward higher latitude, and there's a plasmospheric plumes. This is a TEC plume start to extend toward the polar cap, and at the equatorial plane, you can see the plasmospheric plume has already generated. Although at this time it's kind of symmetric along the x-axis. Then during the late main phase, you can see the ring current has reached its peak value, and the double cell pattern is fully established, and the central convection potential is very strong. And for the ionosphere, TEC plume has extend to across a polar cap due to the strong convection driving. And also you can see there are two channels of erosion depleted electron channel generated. If you map that to the equatorial plane, you can see the size of the plasmospheric plume has been shrinked. So there is some erosion happening here, and also the
Hey, Shanshan, sorry for interrupting you. Can you hear me?
Yes.
Are you using your mouse?
Yes, I'm using my mouse.
Oh, I saw that you are using, but we don't see it on the screen.
Oh, okay. How do I use a pointer?
So I think you can just right click, and there's an option for laser pointer. So if you go full screen first, yeah, go full screen. I think you must be using a mouse when you talk about the structure, but
yes, I'm doing that.
no, you can just go full screen and then right click.
There you can see
Pointer option. Okay.
Yeah, and
Laser pointer. Okay, can you see?
yeah, we can see it now. Yes.
Okay,
yes.
great. Oh, thank you for the reminder. So so you can see there are two electron trough generated at the one is at the mid latitude, the other is at the higher latitude. And if you map this TEC profile to the equatorial plane, you can see one trough is located at the edge of the plasmosphere. Also, the size of the plume has been shrinked or eroded, and the plume has a preferential distribution toward the dusk side than the dawn side. So lastly, it's the recovery phase. The partial ring current becomes a full circular ring current, and double cell pattern has collapsed. And for the TEC plume, you can see the two channel merged into one and cut this plume into and left it with some polar cap patches. So for the plasmasphere, there are a lot of plasma content lost through the day side. So when the corrotation redominant, you can see the size of the plasma shrink a lot because it has lost a lot of content through the day side. So here we first investigate the connection or joint evolution of the plasmapheric and the SED plume. So for this event, here is a UV image at some certain time point during the storm main phase, and we map the TEC observation using the MAGE magnetic field, and we can see the orientation of this plasmapheric plume and TEC plume match fairly well. And here we plot the same thing from the simulation, and we can see this overlapping feature of the plume was successfully reproduced. So the question is, what physical mechanism at play here? So if we look at closely to their evolution, this is equatorial plane and this is ionosphere. We can see the contour of TEC or plasma pulse basically follows the contours of the electric field, and there's a strong electric field on the dusk side of the plasmasphere, causing like it's in dominant, and it causes a down-dusk asymmetry of the geospace plume, and it also causing the erosion or shrinking the width of the two plumes. Also, the expansion of the plumes are driven by the central convection electric field. Also compared with the SEMI-3 RCM simulation, where the ionosphere and the plasmasphere is has a direct mass connection. In our model, we simulate the plasmasphere and TEC in separate models, where we deliberately turn off the plasmapheric refueling. But this kind of joint evolution and spatial synchronization still exists. So we can draw a conclusion here. The electric field coupling is a major cause of the connection between the plumes. So there's no mass connection, but they share the similar set of electric potential, and we still generate this synchronization. So the next question is, what at the mid-latitude on the dark side that contribute to the erosion? So here we plotted a kilogram long 18 MLT from different models. The top one is the sunward or westward ion drift generated by the remix model. Here is the plasmaspheric density profile from RCM, and here is the TEC profile from TiGCM, and delta TEC, which is TEC minus quiet time TEC. So here, first at the initial phase, you can see a single peak. Actually, it is related to the plasma finger that generated here. You can see from the density profile. Then during the storm main phase, you can see in the black box, it's a velocity peak at a higher latitude around 18 MLT, and mid-latitude velocity peak around 45 to 50. So in the purple box, you can see this this velocity peak is causing, or like it's showing correlation of the decrease of this density, or the shrinkage of this plasma pulse location. And in the TEC profile, you can see the one in the purple box causing obvious decrease in the TEC. For the black box, the velocity peak does not interact with plasmasphere. well, it also causing decrease in the TEC, but not quite obvious in the delta TEC though. So we take a snapshot of this TEC profile as well as a density profile in the ionosphere and the equatorial plane. So we can see the purple arrow correspond to the purple box, and the black arrow correspond to the black box. So you can see this this two velocity peak corresponds to the two density trough generated in the TEC, and also this purple arrow point to the location where the plasma pulse is eroded. Also, you can see it more clearly on the equatorial plane that the velocity peak at mid-latitude erode both the TEC and the plasmasphere, while the velocity peak at higher latitude, it erode the TEC only. So we take a closer look at into what happened at 18 MLT. So what I'm plotting here is from the top panel is a region 1 and region 2 current. Also, as well, a second panel is diffuse the electron precipitation profile. The magenta one is diffuse, and the olive one is monoenergetic. Also, we can see the conductance response from those two precipitation. So we can see in the orange shaded area, a part of the region 2 current is not covered by the precipitation. So this will lead to a low conductance region, but region 2 currents still need to be closed. So as a result, there are strong poleward electric field generated. So by definition, this is this velocity peak generated by this strong electric field is a subaurora polarization stream. And at a higher latitude, you can see there's a region without the mono and diffuse, but it's between the region 1 and region 2 current, which they will generate a very strong electric field. This will lead to we call the convection return flow. So this is how this double peak velocity profile generated. Here we also give a reference of the co-rotation velocity. So here we also plotted the plasma pulse location. So we can see the SAPS velocity peak overlap a part of the plasma pulse. This will generate a sunward ion flux, which advect the plasma content out of the area. So so basically that's how the plasma pulse erosion happen on the dusk side. For the TEC profile, you can see the double velocity peak corresponds to density trough or low TEC content in the profile. So for the erosion of the SAPS, Fang Lu has a detailed analysis on her in her 2020 paper that although she used a synthetic SAPS velocity profile or electric field, but it demonstrates that she used O plus as a proxy for the electron content, and by analyzing different source of the O plus, this is from chemical production and loss. This is unbipolar diffusion. This is transportation by the neutral wind, and this is transportation by the E cross B drift. This is a total change of the O plus profile at unit time. So you can see that the erosion on the TEC or ionospheric ion profile is largely contributed by the E cross B transport. So this is also at the large velocity regions, the Joule heating will cause an increase of the ion temperature. This will increase the recombination rate of the ion and electron, so it will further decrease the O plus and electron density at that area. So our result is consistent with Dr. Lu's result, and we do not do the same analysis again here. But for here, we can gain the knowledge that the SAPS transport causes a dust side plasmaspheric erosion and is a major contributor to the mid-latitude TEC depletion. Here is a data model comparison of what happens on the dust side edge of the plasmasphere during the storm. So the top panels shows the DMSP 13 and 15 measurement, and on the left is an earlier pass, and the later is about 1 hour and a half, 30 minutes interval. So for the top panel, you can tell from the disturbance of the magnetic field that measured, you can tell the location of the region 2 and region 1 current. They are separated by the dashed black line, and here is the precipitation measured. This double peak feature is also captured by the measurement, and you can see the SAPS peak corresponds to your trough region in the electron density. And later, this SAPS peak generate a very sharp drop in the electron profile. So if we check this similar results from the simulation, you can see we kind of get the region field line current location right, and we also produce this SAPS and convection return flow velocity peak. And here we are plotting TEC in the navy and the plasmaspheric field line averaged density profile. So you can see this SAPS velocity overlap with plasma pulse, and at a later stage, this is causing a sharp drop in the plasma pulse density profile, which is consistent with the observation. So our conclusion for question 2 is the transport effect of SAPS causes a erosion on the plasma pulse at its dust side and the TEC depletion in the trough region. So for the last question, we're investigating the relationship between ring current and geospace plume development. So what I'm plotting here on the equatorial plane is a different color contour that enclose a region with value that larger than that contour. So basically here it's a contour of the ring current pressure, and the black contour is a plasma pulse. Here the green contour enclose the larger electron pressure, and the orange contour is electron precipitation energy flux. So you can see that the source region of the electron precipitation is embedded in this large electron pressure area. And I also plotted the field line current on the equatorial plane, where you can see that this region 2 current flow into the ionosphere is at the azimuthal front of the ring current, that where the pressure gradient is very large. This causes a distortion of the magnetic field line. It causing this region 2 current. So you can see a part of the region 2 current is not covered by the electron precipitation. This will result in a very strong electric field, which is a SAPS electric field to driving everything toward the day side. So at a later stage, in a later storm, you can see the this strong SAPS electric field. It's like causing everything, causing the plasmaspheric plume toward the dark side, and also it shrinks the size of the width of the plume. So so here we can see that the electron pressure or precipitation is always at the outer boundary of the ring current. This will lead to a persistent SAPS electric field that further causing this erosion. So our next question is, what determines the source region of region 2 and the diffuse precipitation? So so for in the RCM language, so plasmasphere cold iron follows the E cross B drift, but for ring current energetic particles, it has effective electro potential that combines the E cross B drift and the gradient curvature drift. So their effective potential is a combination of the is decided by their first energy invariant for some certain channel. So on the right hand, plotting the plasma content of that channel. So here is the plasmasphere, and this one is the proton channel that contribute most to the ring current, and the electron channel that contribute most to the electron precipitation. So you can see that at a later stage that the when the SAPS electric field has established, the ring current proton can overcome this SAPS electric field and penetrate all the way to the day side to the 2 Earth radii, while the electron cannot overcome this SAPS electric field. Is being abstracted and live outside the 3 Earth radii. So we can so this helps to answer the science question 3. Sorry, this is not 2, this 3. So this is a delicate balance between the energy dependent gradient curvature drift and E cross B drift can self-consistently generate and maintain the SAPS electric field that further shapes the geospace plume. Okay, so here is a summary of the part 1. I won't spend too much time because we got a part 2 to talk about. So here, if you pay attention to the movie I played before, you can see there's a post-sunset channel of a depleted density region generated from the equator during the storm. So so when I was doing the previous storm, I just asked myself what causes this. So actually there are observation for this phenomena during the September 7 to 8 2017 storm. This is reported by HAO in their 2018 paper, that they observed equatorial, they call it equatorial plasma bubble generation from the equator toward mid latitude. So we do a MAGE simulation on this subject. Also, this is plotting the TEC profile in the SM coordinate. You can see this generation of a channel is located at the post-sunset region, and our simulation successfully reproduced this phenomena. So the top panel from the observation here is a snapshot taking at similar time, and as a demonstration that we reproduce this phenomena. So first, we must curious what causes like the seeding of this electron depletion. So what I'm playing is longitude versus altitude, and this is a latitude profile, 3D profile of the O plus density and its a production rate. Here I'm showing the upward E-cross-B drift and the O plus change rate from the E-cross-B transport. So you can see that there's a uplifting of the low O plus region, uplifted from low altitude toward a higher altitude in the F region. So this has been identified as the pre-reversal enhancement. So if we look at the electron density profile, you can see this is located at the evening terminator, and if we can see there's a reversal of the equator where the electric field here is pointing eastward, and this one here, black one, is pointing westward. So this is a classic scenario of the pre-reversal enhancement. So this when this happened, the upward E-cross-B drift will deplete the O plus density, generate low plasma region in the first place. Here, actually, the seeding of it actually is under debate. So previously, people when they report this phenomenon, they call it equatorial plasma bubble. So the bubble is basically generated by Rayleigh-Taylor instability. So here is a famous paper from Joe Huba and Hanli Liu that they use semi-3 vacuum max simulation to simulate this equatorial plasma bubble generation. So compared with our result, we can clearly see that the physical scale of this plasma bubble, or the Rayleigh-Taylor instability, the seeding of it, it's much smaller than what we see in the in this storm. So so here we from the simulation, we draw the conclusion that the seed of it is not Rayleigh-Taylor, it's the pre-reversal enhancement. Then we were looking for the major contributor to the depletion. So we use a similar method as Dr. Lu used in her SAPS study. So we look into the O plus density as a proxy for the electron, and we can see this is unbipolar diffusion. This is E-cross-B transport. This is neutral wind transport, and top the bottom below is the electron, O plus production and loss from chemical reactions. So clearly you can see that, well, this is a total production rate of O plus, and the blue means it has a reduction at the area which corresponds to the trough region. And we can see the obviously E-cross-B transport is a major contributor to the depletion. Then we look into how this E-cross-B transport generated. So if we plot if we plot the storm time variable minus a variable from the quiet time, we can see this this depletion is obviously a storm effect. And here is the delta potential generated from PGCM that you can see there's a eastward, this is eastward and poleward electric field generating westward and poleward E-cross-B drift. And that's how the E-cross-B transport take into action. So and we plotted the E-cross-B drift profile, you can see that there's indeed westward and poleward ECAR speed drift. But we also see the neutral wind profile. It has the same same velocity in that direction. So we need to so this electric field transport may come into two possible process. One is a penetration electric field from the higher latitude. The other is a neutral wind dynamo. So to figure out what's a contribution from both, we do an actual set of experiment that at a certain time point, we turn off the high latitude potential from remix and evaluate the potential generated by the neutral wind instantly. So here you can see if we turn off the high latitude potential, then you can see the black arrow still show the neutral wind, which means neutral wind still exists. But the Thai GCM potential is almost zero. So the difference, this is the bottom panel is the difference when we turn off the high latitude potential input. So there is a obvious difference between the two. And the other experiment is we turn off the neutral wind instant and evaluate the electrostatic potential instantly. So for here, we turn off the neutral wind, so the neutral wind vector goes to zero. And but we still see this potential pattern generated in Thai GCM. So the potential difference by turning off the neutral wind is basically trivial. So we come to a conclusion that the electric potential from the neutral wind dynamo cannot account for the eastward and poleward electric field. And this demonstrates the penetration electric field generated during the storm main phase is a major cause of the O+ or electron depletion in the low to mid latitude. The fate of this depletion channel is during the later stage, you can see that what I'm showing is contour of the diffuse precipitation, and it only covers a part of the region 2, and it generates a very strong SAPS electric field. And this depletion channel later merged into SAPS, and from the production rate of O+, you can see it merging into the SAPS region where the O+ causing depletion at that area. So these two phenomena, the SAPS erosion as well as the post-sunset equatorial depletion channel, depict the dark side storm time ionospheric dynamics as a whole. So this is two separate studies, but they have some interconnections. So here is a summary of part 2, and so here we have MAGE simulation reproduce a post-sunset TEC depletion during the storm, and the depletion is seeded by the pre-reversal enhancement and contributed mostly by the westward and poleward ECAR speed transport. And the eastward and poleward electric field is a result of the penetration electric fields as a storm effect. Basically, that's it. Thank you very much for the attention.
Thank you, Feng.
Yeah.
Okay, that's really nice talk and very exciting results from the latest MAGE simulation. So please, if you have any question, please hand up or just unmute yourself. Ooh. See applause. Let's start with people online. Yes. Bill, yeah.
Shan, could you go back to your slide? I think it was the next to the last slide in 1.3.2.
Okay, this one,
1.3.2.
1.3,
The first, other,
1.3. Okay.
yeah, 1.3.2. I just want to
Uh,
try to understand something. I had a question. Yeah, that one. Yeah.
Mm.
So if you could blow that up, go to full screen. So
Okay.
panel D, I was looking at, whoops,
Sorry.
that's okay. Yeah, okay. So panel D and panel A, I was looking at those two together. And I see in panel D, there's this strong poleward electric field. And that's presumably driving Pedersen currents in the ionosphere.
Yes.
And yet, so what's feeding those Pedersen currents? Because they're outside the region of region 2 current that you see in panel 2, suggesting that there's some other source of them besides the field line currents that we see in panel A.
Okay, so you are asking how this part of region 2 current being connected to?
Well, that strong poleward electric field is driving a Pedersen current, and that Pedersen current has to close. Part of it's obviously closing in R2, but some of it must be closing at lower latitudes than R2. But I'm just wondering what the source of that Pedersen current is at lower latitudes, or am I completely misunderstanding something here?
Okay, so so to my understanding, that well, we obviously see like imbalance of the region 2 current and region 1. So these two current may not be cancel each other because this is during under shielding condition. So this like the region 2 must close in some way that may not go directly to region 1, but maybe to the southern hemisphere, I guess, or like in other way.
Maybe I can chime in here a little bit. So Shanshan, in panel D, where is that E field from? I mean, yeah, which part of the model did you get
This
that
is
E?
from this should be from the remix model.
Remix?
Yeah.
Well, I guess we'll just leave it at the thing. There's something that must be feeding the Pedersen current that accompanies that poleward electric field that is not evident, at least in these diagnostics. It must be coming from somewhere else, some other thing that's not diagnosed here.
Right.
Yeah.
Yeah, for that part, I didn't like concentrate on. I just look for the SAPS velocity peak. So could it be the penetration electric field that so like for this profile, so you're looking at both hemisphere and you can see the penetration effect. Could it be a result of like they close to the other hemisphere?
Well, it could, but then presumably you would see a field line current running between the two hemispheres, but it's not diagnosed in panel A anyway. That contribution to current is not diagnosed in your panel A of that other slide. But I mean, that's a possibility, I guess.
Yeah, because this is under shielding conditions, so you can see we have more downward upward current on the northern hemisphere and less downward, and the opposite in the southern hemisphere. So I would suggest that the current closure may not be like localized. Yeah.
I guess it might be helpful if you can plot, show that convection pattern and show what is the Pedersen distribution in 2D slide. But yeah, we can continue that discussion probably after the talk.
Okay.
Okay, anyway, we don't, I don't want to take up all the time, but thank you, Shan Shan. I enjoyed your presentation very much.
Thank you, Bill.
Okay, thank you, Bill. Other questions? Stop. Okay, Harry.
Yeah, Shanshan, at the end, I mean, the second part, your conclusion is that the electric field, the penetration electric field probably during the storm plays a big role. Does this always happen during storms, or only when somehow that penetration or that high altitude electric field, the eastward electric field aligned with the PRE or the dusk time?
Yeah, I used to have a diagnostic plot, but it's not listed here. So basically I subject the high latitude remix input from the TiGCM output, potential output. So basically you can see a portion of it generated during some time point of the storm. So I mark the region where I see that enhanced penetration electric field. So actually it can be reflected from the solar wind profile. So here, you can see there's a prompt penetration electric field generated here with a sudden drop of the BZ component, and the other is another drop here. So the last one is sudden increase of the RAM pressure. So and afterwards it's a period of southward MF, and it has enhanced penetration electric field along the way. So basically the penetration electric field is a reflection of the solar wind driving from the model, and whenever I can imagine like for some ideal solar wind driving, you can always have undershooting conditions, so you will have penetration electric field causing this pre-reversal enhancement to generate at that location. So to me it seems that let me find this. Yeah, so to me it seems that whenever there's a pre-reversal enhancement happen, and it's located around the dusk side, and where the penetration electric field can interact with this seeding of it, it will generate a depletion channel. So does that answer your question, Henley?
Oh, thanks.
Yeah.
Yeah, one being raised hand, please unmute yourself.
Yeah, just also relate to Henry's question. I believe we look at the TC from haystack, whatever. So this kind of situation happens very often, and clearly it's related to the penetration electric field from high latitudes. So it's another just unique in this storm, but it's occur in other storms too, and also looks like it's happening very often. This case.
Please.
Yeah, Shasha, yeah, very nice talk. But I have a question on the same slide as the second from the last, the ones regarding the penetration fields. So usually, yeah, what plotting? I just wondering what is being plotted here. The penetration field is solved from RCM or from the dynamo solve in the GCM?
So very good question. So so how the TiGCM solve the potential comes from two process. First, we feed the high latitude region basically above 30 magnetic latitude covers that region, because that's a high latitude region where remix of the current continuity equation. Then the neutral wind dynamo will self-consistently generate it, and it will have feedback or contribution to the TiGCM potential through the neutral wind dynamo. So when the system evolved to some states, if you suddenly turn off the high latitude input, you still have this neutral wind dynamo effect remains, because neutral wind cannot suddenly disappear. So it will leave some leave its contribution in the TiGCM potential. By this method, we can see that if we turn off the high latitude portion, this penetration is completely gone. So we just conclude that the neutral wind dynamo cannot contribute to that part of potential.
Yeah, so in that sense, that's basically is the same as GCM dynamo solve. The remix is sort of similar to TiGCM dynamo solve. So it's a numerical effect. But since you are running RCM, so we sort of what being resolved, the penetration fields in the GCM is a numerical results. But in your case, you can. So why not you using the electric field from the RCM? And say compare with the numerical solve from GCM, see how the penetration field look like. Because we suppose that RCM give you physical simulation of the penetration fields, because this is basically depend on how the particle is being transported and the associated with the electric field. So, but in this case, why are you still using the numerical reproduce the penetration field instead of physically produce the penetration fields?
Okay, so I see what you mean. So here in the MAGE model, RCM is as a component of the inner magnetosphere. So its plasma moment will feed back to the MHD model. So the ring current and the field line current generated from the MHD does include the information of the ring current profile. So when it feedback to when the field line current map to the remix solver, it actually includes the information of what's happening in the inner magnetosphere. And in the MAGE model, RCM itself does not solve a potential. It's only RCM only solves its potential when it runs as a standalone model. But in the couple model, we solve this inner magnetosphere driven potential through the MHD using the remix model.
I see. But yeah, I'd be interested. Sorry.
Excuse me, can I just answer your question?
Okay.
So in the MAGE, RCM has a lower boundary condition at 30 degrees, if I'm correct. Wrong, you can correct me. So it still cannot stay the penetration field all the way to the equator. There's a boundary there. So for RCM low, because the simulation is try to look at the penetration electric field globally. So there's still a visible boundary, same as TiGCM. So that's just something we are right now working on global potential solver to remove that. Right now.
But I thought that when Jehovah run the penetration effect, he basically using the electric potential from the RCM feedback into the SEMI.
Yeah, that's I believe I talked to Jehovah. That's he just put RCM all the way to the 10 degrees whatsoever, something like that. But still you need to connect the lower equatorial dynamo with the RCM whatsoever. So
that's right. That is, but when the penetration field usual dynamo is trivial, as Shasha has already shown here. So that's not a surprise. But I just would be interesting to see how these two would appear, even though it's going down to 30 or 20 degrees. But it would be interesting to see how physically the numerically produce the penetration field compared with your physically produce the penetration field.
Yeah, actually, I really like your question. Actually, Samsung is clearly can compare, say, the remix output up to 40 or whatever degree of certain magnetic latitudes now compared to what the TIG SAM gave you
Yes.
from 30 above. Now that is a direct comparison between physics penetration and the numerical penetration here. Yeah, that's actually a very good idea. We should pursue this a little bit further. Yeah,
Okay. Yeah. Thanks, Sasha.
thank you.
Thank you.
Yeah, thank you all for the great discussion. Just for sake of time, people can sign off if you have to go. But if you want to stay and for further continue further discussion with Shanshan, I think we can stay a little bit longer. But other people, you are free to go. So do you want to continue? Okay, sounds like that's good enough. We'll have more chance to meet. Thank you, everyone. Again, thank you, Shanshan.
Yeah, thank you. Bye.
Thank you. See you.